So in some of the earlier videos about money, we talked about, especially in the compound interest section, about taking a chunk of money now and letting it grow, just leaving it alone, and having that balloon up through the magic of banking into some enormous amount of money that you could then do something heroic with, like pay off your mortgage, or buy your kids a house, or just spend it on yourself and trips around the world, whatever you want to do with it. But in those questions, the upfront cost was somewhere in the tens of thousands of dollars. And most of us don't have access to that kind of money upfront when we're 17. So there has to be an alternative. Well, you maybe don't have $17,000 to put in on your 16th birthday, but you might be able to spare $50 a week for a number of years. Now that changes the math, because your first payment gets maximum interest, and the next payment gets maximum less 1 application of interest, and the next one is maximum less 2, etc. But that's a much more manageable savings plan. And if you think about how that's working, you're putting a piece of money in, and you're applying interest over and over and over and over and over again. And then you're applying it to the next payment over and over and over again, less 1, and then over and over and over again, less 2. And you're adding up all those things. So that ends up being the sum of a geometric sequence. So I'm going to start with that formula here. And I'm just going to acknowledge that the R value we're using for finance questions isn't a round number. It's 1 plus the interest rate you're dealing with. So a 1, because you want to keep everything that was there and have an additional amount of money attached to it because of the interest. So if I take this little structure here and I plop it in for R in both of these equations, in this equation up here, I end up with Sn equals A 1 minus 1 plus I to the n over 1 subtract 1 plus I. All right, there's nothing I can do to the top here, because that's all trapped inside a bracket to the exponent n. But 1 subtract 1 is gone, and negative I leaves me with negative I in the bottom. Now I don't like the fraction. Most people don't. So I'm going to pull this out in front here and just write it as A over I. Then we don't have to worry about quite a complicated looking fraction. That I was negative, so out it goes. And I have 1 minus 1 plus I to the n back here. I'd really rather that this equation was not negative. So I'm going to throw that negative into this bracket so that it's not sitting out front. I get A over I. Basically, that's going to switch the orders of this thing. The 1 plus I to the n is now positive, and this 1 is now negative. So I've got a little formula there. I just want to interpret some things. So A was the first term in your sequence. Now that's the amount of money you're paying every month if you're putting money in. So instead of an A, I'm going to use a P for payment. And if you did all this stuff, what would you end up with? Well, you would end up with the total value of all of those payments, each with their individually calculated interest rate applied and then summed up. So that will be the total amount in your account at some date in the future, this many compounding periods away. So if you have a payment plan that is saving up to a large amount, it gets described as the future value, FV for future value. Because it's not worth that now. It will be worth that when the plan is over. So I'm going to take this, I'm just going to write it up here so we have access to it later. The future value of an investment plan is the payments you're making divided by the interest rate times 1 plus the interest rate, exponent n, subtract 1. Okay, which will let me clean this off so I can do some number stuff. Okay. If you're doing it backwards, so instead of putting in $500 each week in order to build up to a massive sum of money, what if you start with a massive amount of money, like buying a house or buying a car, and you're slowly chipping away at that over time? Well, that means that this thing isn't calculating a future value. Right? I don't know what it's going to be worth later. It's going to be worth nothing later because I will have paid off my loan. What I know right now is what I owe today, PV for present value. Now that still will depend on the payments, just like this. It will still depend on the interest rate, just like this. But what's different is I'm going backwards. So these things here end up reversed, and the exponent on this ends up negative. Now, if you remember negative exponents, right? 3 to the negative 1 is 1 divided by 3. So if you are shrinking something, that's what a negative exponent does. It takes a number that would normally make things grow and turns it into something that makes things shrink. So that's why that switched to a negative. Now, you do have enough information, or you have enough, if you had some information to fill into this, you're able to solve for the future value, the payment, and the n, right, the number of terms. So we're going to try a couple of examples here. So what if you are trying to save up? Suppose you can afford $200 a month as an investment. Okay, that's $100 a paycheck. So that is an achievable amount of money for most people. If you find an account paying 6.9% interest per annum, compounded monthly, and you're going to do that for your entire life, for your entire working life. Okay, so if you're watching this video, you are probably in grade 11, which means you are 16. And most people, well, retirement age for your Canada pension plan anyway is 65. So 65 less 18 is, or less 16 is 49 years. Okay, so we're building up here because we're putting money into an account and letting it grow to a large number. So we're using a future value calculation because it's not worth a lot now, but it will be worth a lot in the future. We're going to need to figure out my I value here. So I was quoted to me as 6.9% per annum. That's 6.9 divided by 100, which gives me 0.069. It is compounded monthly, so I'm going to have to take that 0.069 and divide it by 12, and that will give me 0.069 by 12. 0.00575. Okay. Now my end value, right, the number of compounding periods was 49 years. But my payments, and this is important, the payments you're making, right, the $200 a month has to match the compounding period a month. If it doesn't, you have to do a little bit of math and magic to make them line up that way. Otherwise, this formula won't work properly. So just watch that when you're doing these questions. But 49 years, compounded monthly with monthly payments, so I have a nice match here. I'd have to take my 49 and multiply it by 12 months per year, and I end up with 588 compounding periods. Okay, so I'm going to take my build-up equation here. What exactly is the future value of $200 a month at 6.9% per annum compounded monthly if you do it for 49 years? Well, your payment is 200. Your I value is 0.00575. Notice that there's no 1 plus here. It's just the interest rate. This is where the 1 plus happens. To the exponent 588, subtract 1. All right. So first thing I'm going to do is 200 divided by 0.00575, and I end up with 34,782.6087. Now I'm sure there's some rounding error in there, and we're just going to leave it for now. This is looking like 1/100th of a cent, so I think we can afford to be off by that much. 1.00575 to the exponent 588 gives me 29.11684074. Okay, now just to fact check yourself, this number should have grown to something biggish from something around 1. If it didn't, you forgot to put this 1 in there, so make sure you fix that. Means my future value is going to be 34,782.6087 multiplied by 28.11684074. And if I do that multiplication, I end up with $101,286.10. Okay. So this plan will end up leaving $101,000 in your account by the time you're finished here. Oh, that's not right, Jared. I forgot it too. 34782. That's going to make a difference. 4782.6087 multiplied by 28.11684074. There we go. 977. That's a fun number. And 7 cents. That's just shy of $1 million. if you put 200 in a month at that rate for 49 years. So, I mean, the critical question here, if you put $200 a month in every month for 49 years, like how much money did you put in to get this? So just quickly, it was 588 payments of $200. So if I run that, 588 times 200, I end up with $117,600. Now that's a lot of money, but you did it over 49 years. So you built up this massive amount through accessible chunks. But that $117,000, because that very first payment you made sat in the account and accrued 49 years worth of compounded interest, this money in ballooned up to almost 10 times the value of what you put in. So the compound interest thing, it's sort of cute, and you think about how big you can make those numbers, but this is where the real magic is. Because this amount of money, $200 a month, that is something that normal people, right, average people can access. And these are interest rates that normal people can access. And these are timelines that normal people can access. And if you have the forethought enough to try and set something like this up when you're young, it can spit out massive numbers by the time you get to your retirement age. So that's a build-up kind of question. If you know the payment, I'm going to erase this and we'll try a build-up example where you know the amount you're trying to pay off. Okay, so if I want $2 million in 30 years from now, and I have an account paying 7.5 per annum compounded monthly, what's that going to cost me every month in order to build up to that amount? Well, this is the future value, right? I don't have the $2 million now. I'm going to have it later. So I need this thing because I'm saving up to this massive amount of money. So $2 million is my future value. I don't know the payment. I'm going to need these I values. So I guess before I write that down, I should get the I value. So I was 7.5%. Percent just means divide by 100. I'm sure you're tired of listening to me say that by now. Gives me 0.075. Compounded monthly. I'm going to have to take my 0.075 and chop it up into 12 bits because there are 12 months in the year. 0.075 divided by 12 gives me 0.0625. So my future value, the $2 million I'm trying to save up to, is the payment divided by 0.0. Sorry, I'm missing the 0 there. 0.00625. One plus 0.00625 to the exponent n. Well, n, 30 years, but I'm making monthly payments. So n will be 360 payments in total. Subtract 1. Now I don't want this thing in the denominator, it's just causing me stress. So I'm going to multiply both sides by 0.00625. So that number multiplied by 2 million gives me 12,500. This here is 1.00625 to the exponent 360. Which is 625 to the exponent 360 gives me 9.42153395. Subtract 1. 9 there, not a 4. So 1 to 500 is P times 8.421533905. So I just need to divide both sides by this number. I end up with $1,484.29. Okay. Now, 30 years from now, if you're 16 and you're watching this video, that means you would be 46. So that's not retirement age. That's very early retirement age. This percentage, that's more than the percentage that would double your income in 10 years. So that's a pretty good investment, but not impossible. $1,484.29 a month. Well, that's going to end up being $750 a paycheck. Now, trying to come up with that money is going to be tricky. You're going to have to live a very frugal lifestyle. But if you do that until you're 45, you'll be sitting on $2 million in this account. So you can use small payments to build up to huge amounts of money, as long as you have time and a reasonable interest rate. Okay, so that's the build-up type calculations. I'm going to do 2 more examples for you using the paying off version. So we'll do a mortgage and we'll do a car payment, and then I think you're good for the practice problems. So suppose you sit down and you look at your finances and you decide that you can afford $300 a week in mortgage payments. And you find a bank that's willing to offer you a mortgage for 3.9% per annum. So the question then, when you go shopping, is how much money will you have then to spend on a house? Now, there are some asterisks in this. For example, there are some laws about compounding periods, about how the interest has to be calculated, so that banks have some guidelines by which they have to operate. I'm not going to worry about that in this calculation because I think it will distract from the basic calculation here, the same way as this erased I will probably distract from it. There are other rules too, like a bank will only loan you up to 80% of the actual value of the property in their assessment. But again, I'm just going to leave that detail out because I think it distracts from this. So if we can all accept that there are some legal lawyer complications to mortgage, and just sort of set them aside for a minute, this is how the calculation would happen. So what I'm after now is not a future value, right? The future value of my mortgage should be 0 because I've paid it off. This is a present value that I'm hunting for. How much money would I owe the bank now if I were going to pay it off at $300 a week at this interest rate? Oh, I suppose we need a term in here. The bank is offering a 3.9% per annum on a 30-year term. Well, let's make it a 35-year term just so we don't end up with the same numbers over and over again. Okay, so I need an I value. So I was quoted at 3.9% per annum. That's 3.9 divided by 100, which is 0.039. I'm going to be making weekly payments. So this will be compounded weekly, which again, that's not how banks do their business, but just for the sake of the question, we're going to run with it. So I'm going to have to take my 0.039 and split it up into 52 bits because there are 52 weeks in a year. So 0.039 divided by 52 gives me 0.00075. Feels like it's very small, but it will be applied many times through the year. My term was 35 years, but I'm compounding it weekly. So that's 52 payments a year for 35 years. Gives me 1,820 payments. So I'm going to use this present value formula to figure out how much money the bank would give me. So my payments are going to be $300 a week. My I value is 0.00075. These things have switched now compared to that because I am tearing down instead of building up sum of money. 1 plus 0.00075 to the exponent 1,820. All right, so 300 divided by 0.00075 gives me $400,000. And this will be 1.00075 to the exponent 1820. Forgot the negative exponent on there. Let's fix that. 1.00075 to the exponent negative 1820 gives me 0.2555113671. 1 minus that value gives me 0.7444886329 multiplied by $400,000 gives me 297,795.4532, which rounds to 45 cents. All right, so if this is what you can afford per week, $300, and you can find a bank willing to offer you 3.9% per annum with your mortgage spread over a 35-year term, the maximum amount of money the bank will give you is $297,795.45, because this is the amount of money you would buy it for and then be able to pay off at that rate, at this interest, in that amount of time. So about a $300,000 mortgage at that setup. Okay, so I'm going to do one more example where we're going to buy something a little smaller, buy a car, where you know the purchase price of the vehicle instead of trying to figure out how big of a mortgage you can get. And then we're going to calculate what the weekly payment would be. Okay, so we're going to buy a new vehicle for $26,500, which is the manufacturer's recommended selling price, MRSP, of a typical car this time, at this point in time. So if the dealership is offering 3.9% financing on weekly payments, over a 6-year term. Well, we've got a large amount of money now. So that's a present value. Not a future value because the amount I owe on the car, hopefully in the future, is 0 because I will have paid it off. So it's not one of these. It's going to be one of those. I'm going to need an I value. I've got 3.9%, which is 3.9 divided by 100, which gives you 0.039. So on weekly payments, so I'm taking that 0.039% and I'm splitting it up over 52 payments. Each year, 0.039 divided by 52 gives me 0.00075. Yes, it does. Okay. My N value, 6 years worth of payments every week. 6 times 52 is 312. I'm just going to fact check myself there. Good. So I've got enough information to dump everything in here. The present value of the thing I'm purchasing is $26,500. I don't know what the payments were going to be, but I know my I factor is 0.00075. And I need 1 subtract 1 plus 0.00075 to the exponent negative 312. Remember my negative this time. So first off, I want this out of the denominator, so I'm going to multiply both sides by 0.0075. So 26,500 multiplied by 0.00075 gives me $19.87.5. Got 1.00075 to the exponent negative 312 here. $1.00075 to the exponent negative 312 gives me 0.791431262. One minus that number gives me 0.208568778. Where are my counters? There's a P in front of all these. So I just need to divide this by this. And I get $95.29. So in order to pay off a $26,500 vehicle at 3.9% financing over 6 years, you're going to have to spend $95.29 per week. It's sort of an important question there. How much money is that? Well, 95.29 multiplied by 312 payments gives me $29,731.20. So you will have ended up spending $29,731.20 on a vehicle that you only purchased for $26,500, which, and that should make sense. If they're charging you interest, you will have to pay back more than what you borrowed in the first place. Is $3,200 over 6 years a lot of money? Well, if you don't have this and you need a car, right? You're going to have to pay for the privilege of borrowing that money from the dealership. And that's just how the world works. So, tiny payments can pay off large amounts of money over time, as long as you factor in your interest rate there. I think you've seen an example of future value, present value, and the payment calculation for both building up and paying off type calculations. So I think you're good to go